Okay, can folks in the chat hear me? Wonderful, thanks. Okay, how's everybody doing? All right, so as always, don't forget the seating survey, upcoming deadlines, today's content videos. There are 5 of them. Friday, 3-part homework, and the small group activity number 3 is now out and available, due next Tuesday. This one is dealing with first order kinetics, specifically relating to the to radioactive decay and how geochemists use it to determine the age of minerals of various kinds. So do we have any logistical stuff before we move to content? Okay, so I'm anticipating being able to get the content videos for next week up today. And so that means that shortly after that, I will be working on getting some example type problems that are going to be sort of exam style for some of the kinetic stuff out to you, as well as catching up on some of the back grading stuff. So look forward to that sort of thing and hold my feet to the fire to make sure I get you what you need. Okay, there were not very many muddiest points that were brought up on Piazza. One of them was pointing out an error in a video. This was not a quiz question in the video. In the elementary reactions video, there are actually 2 places that there are mistakes. One of them is this, where we go through an argument talking about the carbon monoxide concentration and the idea that if we double the carbon monoxide concentration, we would double the frequency of the collisions, and so it makes sense for the order of the reaction with respect to carbon monoxide to be 1. I then say that's the same thing for carbon monoxide, which I just had talked about. So that's supposed to be the same thing as for oxygen. So anybody that was confused by that, you were right to be confused by it because I repeated myself. There's another error in there that I have not fully figured out yet. There was a place where I give an example of a multi-step mechanism that has a different reaction order from what you would predict if it were a single-step mechanism. We do not go into figuring that out until later videos when we talk in the kinetic mechanisms video. But somebody pointed out that when I listed the reaction, the overall reaction, and then I listed the steps of the mechanism don't add up to the overall reaction that's listed there. That's because partway through, I discovered that one of the reaction mechanisms I was looking at to use as an example, I had incorrect, and so I picked a different one, but apparently I didn't find all the places that I put it. So if any of you were looking at that particular example and confused as to why, what's going on with those, that is a mistake. So it doesn't affect the argument that's going on right then because we don't go into the analysis there. We don't do that until a later video. But know that that is in fact a legitimate mistake at that point. Okay, the only real content question I got on the muddiest points was from the activity. And there was the comment that in one of the questions that you can separate different isotopes by their masses. And the question was, how do you do that? Because one of the things that you learned, I hope, in Chem 111 is that chemically, there's not a difference between the isotopes. So if you have one isotope of carbon and another isotope of carbon, they have the same chemical properties. The difference is in the mass, is in the mass of the nucleus. And so what is done in order to do that, and I'm not going to hold you guys responsible for this, but getting a sense of what's going on with it can be useful. What's generally done is that you'll take a U-shaped tube and then fill it with a fluid. So this is like a test tube, but it tends to be a lot more sturdy than that. You fill it with a solution of a very dense solvent. So something like an aqueous solution of cesium chloride is a common one, because cesium, you know, is pretty far down the periodic table, and so that increases the density quite a bit. But you fill it up carefully so that there's more cesium chloride at the bottom than there is at the top, so that this area down here is very dense. This area up here is less dense. You then take your, say, uranium isotopes that you're interested in, usually in something like an oxide, so you make UO2, and you have multiple isotopes in it. You put it into this sample, into this container, and stick it into a centrifuge. What a centrifuge does is it takes this and then spins it really fast around, so that there are very strong forces, centrifugal forces that are pushing this way. And what happens when you do that is that anything that's dissolved will migrate to the height where the liquid is the same density as the particle you're dealing with. So what that means is that if you have two different isotopes of uranium, they will go to slightly different positions in this tube. And so you can then come in and very carefully stick a pipette down here and pull out this layer, and then take a different pipette, stick it down here and pull out this layer. And you're able to separate the isotopes this way. This, you may have heard back when people were talking about the justification for, I think it was the invasion of Iraq at one point, when there was talk about centrifuge tubes that had been discovered that the Iraqis were getting there. And the reason that was an issue was because it's exactly those kinds of centrifuge tubes using a mechanism just like this that people use to enrich uranium in the more radioactive isotopes for use in either nuclear power plants or for nuclear weapons. And so because this is such a necessary step for any kind of enriching of a specific isotope of uranium, things like that, like identifying how many centrifuges have you bought, how many centrifuge tubes have you bought, are they the style that is necessary to go to the really high speeds that you need for this kind of separation. Those are things that are used by the international community to try to determine if a country is breaking agreements about enriching uranium and such. So at any rate, that's the general idea of how isotopic separation is done. And that was the only Muddiest Point question that I had on Piazza. So I am happy to talk about any content that anybody is confused about, would like me to give a reintroduction to, if you are just feeling lost on it. Absolutely anything. What do you guys want to do? Yes?
Can you go over how the kinetic and potential energies change over
over the activation barrier. Yeah, absolutely. Okay, so the question for the folks in the chat is going over how the kinetic energy and the potential energy are changing as you go over the barrier. So let's orient ourselves to this plot. So we have a reaction coordinate, which is also known Okay, so Zoom folks, it looks like we disconnected for a minute. Can you hear me at the moment? Okay, cool. All right, so generally we start off by just plotting the potential energy here. And so if we have the reactants at this point, and the products over here. And so the example I am showing here, the products are at a higher energy. So our delta H is greater than 0. And so this would be what? An endothermic or an exothermic reaction? Endothermic, that's right. And then we have some reaction barrier in between. The height of this relative to the reactants we call EA, which is the activation energy, and this configuration of the system is known as the transition state. Okay, so think of this like like an actual physical hill. And you have maybe a ball, one of the elementary school kickballs or something that you are trying to roll up the hill and get it over the hill. It's all about how high you are, right? And so you need a certain amount of kinetic energy in order for the ball to roll up. And if you don't have enough kinetic energy, then it won't be able to make it all the way over. So that's it's a very, very close analog to what we're talking about in this case. So the idea here is that if we start with a total amount of energy, so I will use red for, if we start with this amount of total energy, that means that this amount right here is the kinetic energy, and then this to wherever our arbitrary point of 0 is the potential energy. As our ball rolls up the hill, as it's going up, what we have is the kinetic energy is getting converted into potential energy. The total amount of energy you have stays the same because of the conservation of energy principle. You can't create or destroy energy. It only gets converted from one form to the other. So at this point right here, you have less kinetic energy and more potential energy. So the ball has rolled part way up the hill. It is now moving slower because it has lost some kinetic energy and put it into the kinetic energy, put it into the potential energy. When it gets all the way to this point, all of the kinetic energy has been converted into potential energy. If you have no kinetic energy, that means it has stopped moving. There is no speed to it, and it's the highest point it gets to. At that point, you have potential energy and no kinetic energy, and it's sitting there on the side of the hill. It's going to start rolling back down. It's going to regain its kinetic energy as it goes back down this way. So at that, what happens then is it comes back and you now have that kinetic energy back, but now the particles are moving apart from each other. In the ball case, the ball is now rolling past you, going the other direction. In the molecule case, in the reaction case, what's happening is that the molecules are coming together. As they start to get close together, they are starting to feel some repulsions from each other because they're beginning to get too close, all right? But they don't have enough energy to get all the way to the transition state. And so at that point, they stop moving, and then they start moving away from each other because they're repelled. And that's what's going on here. If, on the other hand, you have this much total energy that you're starting with, so that your kinetic energy is even higher, the same process is happening, but you'd never fully run out of kinetic energy. Even when you get to here, you still have a little bit of kinetic energy, which can carry you over the top of the hill. So it's moving along, slows down, passes over the transition state, and then continues on, speeding up as it goes down the other side. And now you have the products that have kinetic energy that is as they escape each other. And how much kinetic energy do they have? That amount right there. Does that help visualize what's going on in this system? Yeah, okay. Any clarifying concepts that we can dive deeper into? So I could go on and talk, if you would like me to, about the connection between this and temperature. Would that be useful? Yes? Okay, let's do that. So the idea on connecting this to temperature, and we talked about this back when we were looking at vapor pressure of a liquid. We talked about how there is this thing called the Maxwell-Boltzmann distribution of speeds, of molecular speeds. And what we get, what we're doing here is we're plotting the fraction of molecules that have a particular speed at different temperatures. And so we'll say blue is cold. We will say green is warm. And we will say red is hot. Okay. And we're not going to go into the proof of what this shape looks like. That would be sort of a P-Chem kind of thing we would do, but it's not a Gen Chem thing. The shape's going to look something sort of like this, and it's going to have a long tail. The green one, for the warm one, is going to be shifted out some, and the tail's going to be bigger. I didn't draw that very well. And the red one's going to be shifted out even further because there are going to be even more molecules that have higher temperatures. Where we used this before was talking about the intermolecular attractions that are holding the molecules to a liquid between the, so if the molecules on the surface of a liquid, you have intermolecular forces that are attracting them back into the liquid, and so you have to have a certain amount of kinetic energy, a certain amount of speed for the molecules to be able to escape those attractions. And so whatever that speed is a threshold. Okay, and so what we can see is that there are a few molecules in the blue case that are above that threshold. There are more molecules in the green case that are above that threshold, and there are a lot more molecules in the red case that are above that threshold, which explains to us why at higher temperatures, the vapor pressure of a liquid is higher. Okay. Well, here we're talking about exactly the same concept of a threshold. Only instead of it being the attractions of the molecules to their neighbors, we're talking about the activation energy for the reaction happening. So it's exactly the same idea as this. It's just now talking about a different type of threshold. And so what we expect then is for us to have the same temperature dependence for a reaction rate as we would for the temperature dependence of the vapor pressure. And in the content video on this, I took what was called I believe the Clausius-Clapeyron equation, which you are able to write as, let me get another sheet of paper. The vapor pressure of the liquid over the liquid equals some constant times E to the minus delta H of vaporization over RT. So this is an alternate form of the Clausius-Clapeyron equation for the vapor pressure of a liquid. What we did was we said, okay, let's do exactly this same thing, but talking about our rate coefficient. We're going to have some constant coefficient, E to the minus activation energy over RT. So we're still talking about some kind of threshold. we still have some kind of scaling factor. In the case of the vapor pressure, that scaling factor depends on whatever reference pressure we're using. So we would figure that out by doing something like, we know at the boiling point, the boiling temperature, we know that the vapor pressure equals the surrounding atmospheric pressure. And so you can go through a procedure to figure out what C would be from that. In this case, this is the frequency factor, or the Arrhenius factor, which includes in it the fraction of the collisions that have the right orientation for the reaction to go on. But this part here is exactly the same, just with a different threshold energy that is plugged in. And this expression is exactly that. It is telling us what fraction of the molecules, or what fraction of the collisions in this case, have energy in excess of this threshold. So what that means then is that we are using this mental picture of what the process of a reaction looks like to make a prediction about how the rate of reaction should depend on temperature. And that prediction is actually really, really good. We get very good agreement for almost any rate constant you can come up with to this functional form. All right, any clarifying questions on any of this? Okay, so a question from the chat. Can we also talk about how you'd be phrasing these concepts in a test-like format? So this part of it I have not written yet, so I don't know for sure. But I could certainly give you some kind of reaction diagram like this and ask you to identify or label parts of it, similar to identifying or labeling parts of the phase diagrams in the previous exam. I could pose hypotheticals to you about to describe what is going to be happening to a system as it's approaching and either going over the reaction barrier or not. So you could imagine, for example, me saying you start with a kinetic energy such that the total energy is in excess of the activation energy. Now, order the steps of what's going to happen. Well, the molecules will approach each other, would be like the first step. The kinetic energy would decrease, but not all the way to zero. You'll hit the transition state. There will still be some kinetic energy left to be able to go over the barrier. Once you're over the barrier, once the system's over the barrier, kinetic energy will increase, pushing the products away from each other and continuing on towards products. I could also, what I've described here is the bimolecular version. I could ask some questions about how this picture is the same or different based on a unimolecular process or a termolecular process. So in the unimolecular process, the idea is that the kinetic energy you're talking about in this region isn't the relative motion of two particles that are coming in towards each other, but rather it would be vibrations within the molecule that it has. So you might imagine the molecules, the atoms in a molecule as kind of being on springs. And so if they're vibrating really violently, then it could vibrate itself apart and cause a dissociation step to happen. That could happen in a unimolecular way. Well, how does the molecule get that much kinetic energy? Well, it gets it by collisions with other molecules, where it collides with something that's moving quickly, and that transfers some of that kinetic energy from the translational motion into vibrational motion, would be how that would work. But then it's happening with just one molecule going across it. In the termolecular case, the idea typically in those cases is that the product, if it were bimolecular, would be a single molecule. And so the issue is that if two molecules come together and are forming a bond over the course of the reaction, you still have that excess kinetic energy at this point. And that's a problem because all that excess kinetic energy is stuck there in the vibrations, which means that it's going to break itself apart and go back over here back to reactants. So if the reaction is going to continue, you have to have some way for that excess kinetic energy to get carried away. And so that would get carried away by having a third thing come in and hit it at the same time. And then that shoots off with the excess kinetic energy, leaving the single molecule at the end here without enough kinetic energy to get back over the hump, back towards reactants. So those are the kinds of things I could see asking about in this kind of question. You could also imagine some things like, I'm trying to think outside the box here. How can I ask a question that might see how much you understand the concepts rather than just reproducing problem types you've seen before. So remember that we've talked a little bit about a dynamic equilibrium, which basically means that if you have a reaction that goes forward, you could also have that same reaction going backwards. So from this kind of picture, imagine that this reaction is a reversible reaction so that you could get a dynamic equilibrium going on between reactants and products. In this picture, what can you say about the activation energy for the reverse reaction compared to the activation energy for the forward reaction? Is it going to be larger or smaller? Smaller, right. So the activation energy for the reverse reaction would be this right here. Right? So that's sort of an example of how you might start to try to combine some concepts from what we're talking about. And yes, people in the chat had the same idea. It would be less, it would be smaller. That's right. Okay. There's also the possibility, so I'd mentioned that I was going to be getting you a spreadsheet that would let you run some simulated kinetics experiments, and then I'd give you some tutorial videos on how to, within Excel or something like that, do some analyses of the results from that. You could imagine that I could put in there a temperature variable as well, so you could run the experiment at different temperatures, which would allow you to use this equation here to find the activation energy and the Arrhenius factor. Okay. So what you would do there, generally the easiest thing to do is to find a linearized form of this, and since the activation energy and the temperature are in the exponent here, you would do something like natural log of K equals natural log of A minus EA over R times 1 over T. And so then you can see that if this is Y and this is X, then you have an intercept of that and you have a slope of that. So if you ran the experiment at 3 or 4 or 5 temperatures, you plotted the natural log of the rate coefficient versus 1 over temperature, then and did a linear fit to it. And I'll show you, when I get you this spreadsheet, which I hope to do this week, to get you this an example version of these spreadsheets, I'll show you how to do that within Excel to find out what a linear plot looks like and extract the slope and the intercept from that kind of thing. And so that would let you determine values like this. What else can we talk about? Or I'm happy to keep going on this if anybody has further things they'd like me to talk about on it. Intermediates, somebody says on chat. Okay, so intermediates are something that show up in a mechanism. So the idea would be we have some kind of mechanism I don't know, I'm making things up. All right, let's just do this. So if we look at our overall reaction based on this mechanism that I've proposed here, we have 2A plus 2B plus C plus D goes to C plus D plus E. Well, we have the C's on both sides, we have the D's on both sides, so this is 2A plus 2B goes to E. So the C and the D show up as part of the mechanism. They are produced by the mechanism and then destroyed by the mechanism. So they are intermediates. There is another kind of thing that can show up in the mechanism but does not appear in the overall reaction, and that would be a catalyst. But that would be something that you start out with rather than something that is generated by the reaction itself. Okay, so that's the distinction between an intermediate and a catalyst. The issue with intermediates is that you do not want to have intermediates in your overall rate law. Because if you do, it's not very useful, because it's not something you can control as you're setting up the experiment to run it. You can't say, okay, this is the reaction I'm doing, now I'm going to start with an initial concentration of 1 molar of C. Now C only shows up when it's created over the course of the reaction. It's not something you can introduce into the system. So your overall rate law should not have your intermediates in it. So when you go through this process and you say, okay, what's my rate determining step? Let's say this one is the slow step, so that's the rate determining step. Then you know that your overall rate is going to be, do K3, K2, K1. It would be K3 concentration of D, concentration of A. Concentration of A is okay to have. Concentration of D isn't. And so you have to find some ways to get rid of the D as you go through it. And to do that, you have to make some approximations of some sort. And you would be told which approximation to use. Or is it, I've introduced 2 main approximations so far. Well, I will only introduce 2 approximations in this class. I'm not going to introduce other ones here. I've introduced the steady state approximation, and I've introduced the pre-equilibrium approximation. In this case, I did not write any of these as equilibria, so you would not be able to do the pre-equilibrium approximation here. So the only one that would make any sense to do would be the steady state approximation. Okay. So at any rate, that is what an intermediate is, and that's why you need to get rid of it from the rate law. Yes?
Can we go over how to do the steady state approximation?
Sure. So the steady state approximation says that for an intermediate, the concentration of that intermediate, in this case we'll assume D, is not changing much. With it not changing much, what we mean is that the rate of creation of it equals the rate of its destruction. So what we would do is say it's created in step 2. So we can write down that that rate is K2 concentration of C concentration of B. The rate of destruction is going to be K3. So that's going to be K3 concentration of D, concentration of A. D is the one we're worried about at the moment. So we're going to label that as being a steady state concentration. And we solve for it. So just doing some algebra, D steady state is going to be K2 over K3 times concentration of C, concentration of B over concentration of A. And now this can get plugged in over here, and you now have your rate law no longer having a concentration of D in it. Does that general idea make some sense? Okay. Now, in this particular example, the result will have a concentration of C in it, and C is also an intermediate. So you would do this process again for the creation of C, a rate equaling the destruction of C rate. Solve for C, plug in for that, and then you would have a rate that only is going to have A and B in it at that point. This particular one, because this particular mechanism, because I was just coming up with this mechanism off the top of my head rather than looking at a real one, would be an example where, assuming this is the rate limiting step, and assuming the steady state approximation would be contradictory assumptions. So I would not throw this particular example at you. But the procedure here is the procedure you would use for the steady state approximation. And I would give you an example where the steady state approximation actually was something that makes sense. And again, you would not be expected to know that particular detail. You would not be expected to look at this and say, yeah, those two things are going to contradict each other. So does that help with understanding intermediates? Okay. Wonderful. Okay. What else can we talk about? So there's a request from the chat to go over the diagram of phase changes again. I'm happy to do that if people don't have, are you talking about stuff from exam 1 material? Okay, so I want to make sure that, if people have questions on kinetics, stuff, I want to do the kinetic stuff first because that's what the current material is, but if we run out of kinetic stuff to talk about, I'm happy to go back to that. Somebody's saying, before you disconnected, someone mentioned in chat collision theory and someone else asked for half-lives. Okay, so the collision theory was this stuff that we talked about right here. And so collision theory is essentially has two parts. The first is modeling reactivity as being based on individual collisions. And so as a result of that, when you have a reaction that is just a single collision, you can write down the rate law just by looking at the stoichiometry. So if you know it's a single collision, and if you know it's A plus 2B goes to something, then you can immediately write down that the rate is K concentration of A, concentration of B squared. Okay, so that's the first part of collision theory, is if you know it is a single collision, then you can do this. So same thing as an elementary step. The second part of collision theory is this analysis here about the reactions proceeding by way of a transition state, which has an activation energy associated with it, and that activation energy tells us about the temperature dependence of the reaction rate. And we just went into that in quite some detail. So that's what collision theory is. The second topic that you brought up here is half-lives. So the first thing I want to mention on half-lives is that the video on half-lives does the analysis for 3 cases. It does the analysis for the 0th order case, the 1st order case, and the 2nd order case. And we found that in the 1st order case, the half-life did not depend on the concentration of the species. It only depended on K, which means that in the 1st order case, if you know the half-life, you know the K. If you know the K, you know the half-life. The 0th and the 2nd order cases do depend on the initial concentration. So while you can still talk about a half-life in the 0th and the 2nd order case, it's nowhere near as useful as it is in the 1st order case. Because for a 1st order case, as you've seen in the small group activity, you can just say the half-life of this uranium isotope is 10 to the 6th years, something like that. And that tells you the rate constant right there. You cannot do that for 0th order and 2nd order case. And so it is ridiculously rare for anybody that's a practicing chemist to talk about a half-life for anything other than a 1st order case. So that's the most important thing there. Now, in the 1st order case, the basic idea is very simply write down the 1st order rate law. So you can do it either in the standard integrated form or the linearized form. Doesn't really matter which way you go. Because I remember it easier, I'm going to write the standard version. And you plug into it what a half-life means. A half-life is the time it takes for the concentration to become half of the initial concentration. So let's just do that. So the concentration becomes this. And because we have said the concentration becomes that, the time we're talking about is T1/2. Now it just comes down to solving for T1/2. And this is just algebra. The A naughts cancel. So we have 1/2 equals e to the minus k T1/2. And right there we can already see that the initial concentration is canceled out and is gone from the equation. So we need to get something out of the exponent, so we take the natural log of both sides. So natural log of 1/2 equals negative k T1/2. T1/2 equals negative natural log of 1/2 over k. Well, one thing you can do with the logarithm, if we have a times the log of x, that equals the log of x to the a power. Well, this negative here is basically the same as being multiplied by -1. What's 1/2 to the -1? Negative 1 power means you take a fraction and you flip it. So this is natural log of 2 over k. So what we have here is a relationship between t1/2 and k. Now notice what this means. This means that we can take our rate law here and we can write it, instead of using k, we can write it using the half-life. So if we look at this expression here, we can rewrite this as k equals natural log of 2 over t1/2, just swapping the k and the t1/2. So we could write a equals a naught e to the minus t times natural log of 2, is that on screen? There we go, over t1/2. So this is just algebra at this point, right here. And so if you are given a half-life instead of a rate constant, as you are in the small group activity, then you can either convert the t1/2 to a rate constant and use your rate constant equations here, or you can change your rate constant equation so that you're dealing with the half-life instead. Lots of different ways to go about it. So does that help with half-lives? Okay. All right. Anything else on kinetics? Seeing some shaking of heads. All right, so if not, I'm happy to go back to the chat request to go over diagrams of phase changes again, if people would like to. So can you tell me what exactly you're looking for, Madison? Are you talking about phase diagrams themselves? Not getting an answer on that. So I'll start talking about it, and if I get a clarifying response, I'll move in that direction. So the general idea is that we have a pressure versus temperature plot. Generally, we will have something that looks like this. At high temperature and low pressure, what is the phase that we would expect to have? Yeah, gas, right. At high pressure and low temperature, what would we expect to have? Solid. And in between, we will have liquid. Oh, liquid, great, liquid. All right. So within a region, you have a single phase, and by changing the temperature or changing the pressure, you basically stay within that phase. You've just changed the conditions of that phase. Along a line, you have two phases in equilibrium with each other. And so that's how you get a phase transition going from one phase to another, is by crossing that line. So as you go, say, from liquid to solid this way, say we're doing a cooling curve there, you start fully in liquid, you hit the line at some point. Right when you hit the line, it is still all liquid. As you continue to remove heat from the system, it is transitioning but staying at that same point on the phase diagram is transitioning from liquid to solid, so it is freezing. By the time all of it has frozen, you've now removed even more heat, and then it can start to cool down to go over to the solid side. So that's the general idea of these phase diagrams. So in a region, you have 2 degrees of freedom. Along a line, if you're wanting to stay at the equilibrium between the two, if you change the temperature, you're also going to have to change the pressure, for example. So you have 1 degree of freedom as you go along there. And then at the intersection, there is only the single point where all 3 are in equilibrium with each other. I have no idea if this is addressing Madison's original question or not. Okay, you're welcome. Is there anything you want me to clarify about it or go into more detail on? Okay, nothing else. So we have about 10, 15 more minutes if there's anything else anybody wants me to go into. Yes?
So for the intermediates, you said there was the steady state and the pre-equilibrium.
The pre-equilibrium approximation, right. So I think the pre-equilibrium approximation is the one that the textbook goes into. And so the pre-equilibrium approximation is the one that we used when we talked about going from gas phase kinetics to solution phase kinetics. And so that, let's go ahead and just use that example. So if we have, we call this KD, we call this K minus D, and this is our encounter complex here. And then the encounter complex goes on to products at some reaction rate step. So the pre-equilibrium approximation is saying that when you have a reversible reaction that is fast compared to a later step, then that means that the forward reaction equals the rate equals the reverse reaction rate. So it becomes an equilibrium, a dynamic equilibrium between this and this, which is slowly being bled off by this step right here. That's the idea of a pre-equilibrium. And so the way we would analyze that, so I'm going to go ahead and mark this as fast and this as slow, meaning this is the rate determining step. So the way you would analyze that is to take the forward reaction rate. So can someone tell me the reaction rate, how I would write the reaction rate for the forward reaction? Go ahead. Yep, that's right. Perfect. KD times concentration of A times concentration of B. And we want this rate to equal the reverse reaction rate. Can somebody tell me that one? Go ahead.
K negative D, AB.
Mm-hmm. Right. Now, where we would use this, I should have done another step before this. I should have written down what the overall rate was. Our overall rate is the rate determining step, the slow rate. So that is going to be concentration, excuse me, Kr times A dot 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 B here, but we don't want this, right? Because that's an intermediate. We don't want the encounter complex as part of the reaction rate. So we take this and solve it for the concentration of the encounter complex so that we can plug it in here. Hopefully you can do that in your head, so it's just going to be this with the K minus D in the denominator. So this now becomes Kr times Kd over K minus D times concentration of A times concentration of B. And we now have an overall rate law that only depends on the reactants, no longer depends on the intermediate. And so as a result of that, it is now a useful rate law that we can use in a reaction, in a particular experimental problem that we're trying to solve. You can, I think there was an example in the content video where there were two pre-equilibria going on simultaneously. So this is the kind of thing that you can use multiple times in a single problem if there are multiple equilibrium steps that you're dealing with. And it's very analogous to the case we just looked at on the steady state approximation, where we were doing we had two intermediates we were trying to get rid of.
Can I help you all? Cool.
Does that give you enough to work with on how to use this pre-equilibrium approximation? Okay. Anything else?
Thank you.
Yeah, have a good day.
See you in 2 weeks.
Cool. Great law for
All right, well, we can call it for today then. Thank you all very much.